Hey everybody, this is to work through some of these 13.4 quadrilateral proofs. And before I even move on here, I just kind of want to give you guys a little bit of heads up as far as how important proofs are. It turns out that for your higher level classes, you're not going to find that you run into these very much. They put them in a geometry curriculum mainly for the portion of learning how to logically put an argument together, connect all the dots. They're considered an important part of your learning experience, but I don't really test a whole lot and put a lot of emphasis, as much emphasis on these as maybe some people would, mainly because you're going to find that the algebra review that we're doing right now and some of the other skills that you've been learning and practicing are going to become far more important next year. So if you do move up in higher level math, being able to put proofs together can become important, especially if you become a math major. But most of the time, you're really not going to run into a lot of proof building skills being necessary for, say, even all the way up to, say, second, and third level of calculus. Okay, so whereas algebra will be very important for that. Okay, so we do spend some time with these, being able to do this kind of thought process, the thoroughness of the thought process, being able to be creative in terms of coming up with the steps. All of that does have a place in the geometry curriculum, but you are not going to be tested very heavily on this, okay? So do the best you can to follow along and to be able to build your skills in this way and just learn something from it, okay? So I'm going to do the very first proof in this section, which says that if we have opposite angles of a quadrilateral, and if those are congruent, well, then we're going to say that that quadrilateral must be a parallelogram, okay? So since I'm looking to try to prove something looks like a parallelogram, I might as well draw something that looks like a parallelogram, right? So I'm going to kind of sketch this out. And okay, so that looks pretty decent. And it told us that the opposite angles are congruent to each other. Okay, so I'm going to kind of do it this, I'm going to mark it this way. And in fact, in the spirit of, I know where I'm going with this, and this is kind of where get a little bit of background. I could do some numbering, but because I'm going to be using this equality, I think I'm going to go ahead and call both of these guys X's and both of these guys Y's, okay? Since they're going to be equal, and if I'm already thinking to myself, I'm going to be using some algebra with these, I can label them X's and Y's, and that's because I already thought through my proof, and that's the direction that I'm going to go. Okay, so as with every proof, I'm going to start with something that's given. You need a seed, right? And so I have to label. I'm going to give these a little bit of a label. Okay, so my number one step, angle A is congruent to angle C, and angle B is congruent to angle D. Okay, so those are both my givens. That should make sense. Okay, and then, okay, so let's talk a little strategy before I write anything down further. Okay. I've been given this equality. Basically, the measures are equal, the angles are congruent. And one of the things that I think I'm going to rely on here is that if I were to cut this in half, and I'm really not happy with that line, I'm going to use a little bit of a straight line to do this, okay? But let's just say I drew a perpendicular line, down this way, okay? And let's just say that if I were to look at those as 90-degree angles, what I would hope you would notice is that X plus Y are supplementary, right? If I add those, the measures of the angles together, right? Measure of angle A, or I could actually say X plus Y because I've given them an algebraic. The measure of angle A is X, and so on. And so there is a theorem, and I'm actually going to go over and do a share over to the postulates and theorems page here, okay? And there's something called the interior supplements theorem. And what it does is it states, this is on page 2 of your that if two parallel lines are cut by a transversal, then the interior angles on the same side of the transversal are supplementary, okay? And if I know that, then I would actually be able to prove that they are parallel, which will then be able to prove I've got a parallelogram, okay? So this one's not actually very cut and dry, especially for a number one proof, but that's kind of what I'm going to be doing. And then we also have this converse that would state that if two lines are cut by a transversal and those angles are supplementary, then the lines are parallel. So I'm actually going to be using this one. This is one we haven't used very much, if at all, up to this point. So it's really going to be more about using this with quadrilateral proofs. Okay, so I'm going to go back over to the whiteboard here, and we're going to decide, we're going to actually kind of look at that idea here as we're going through this proof, okay? All right, I'm going to start with saying, well, I have to first define that x is equal to the measure of angles A and C, and then y is equal to the measures of angle B and D, okay? So I can do that by algebraic substitution, okay? Substitution. All right, that's a good enough justification for that. And then I'm going to say, well, if I could say, just looking inside, right, that 2 of my x's plus 2 of my y's add up to 360 degrees, right? And what tells me that is the quadrilateral sum theorem, okay? We've already proven that, okay? And then once I know that, then I could divide everything by 2 to get x plus y are equal to 180 degrees, right? And that's just by division, right? Our division property of equality. Okay. Now maybe you can see where I'm going. If that's true, well, then I could say that angle A and angle, let's see here, not angle A and angle C, angle A and angle D, okay? And then angles, let's see, we've got C and B, right? Angle B and angle, let's see, C are supplementary. Okay, and that's by definition of supplementary. If they add up to 180, then they are. Don't comment on my handwriting on the little whiteboard here. Okay, all right. Then we could say there then that if these are supplementary, this is where we're going to pull out that theorem, okay? Because we have pairs of supplementary angles, this is the key, okay? We can now say that DC is parallel to AB, okay? And AD is parallel to BC. And this is by the converse of the interior supplements theorem. That one might be faster to type one in a box. Okay. All right. Well, given this far, am I there? Let's see, I'm going to mark. Well, I think I am, because I can get rid of this. That was just for show, but on my actual diagram here, right, I can now state if this is true and if this is true, right? Well, then I have a parallelogram. I'm there. A, B, C, D is a parallelogram, and that's what I wanted to prove. Let's see, parallelogram, right? And that's based on the definition of a parallelogram. How's that? Okay, all right. So that's kind of a classic proof, and I think the idea here is to identify. These can be really difficult if you don't identify something like this here, right? That that if I can follow this through, I can make, with this one statement, I can actually save myself an awful lot of time. There are many, many other ways to prove this, but they could take an awful lot more time. This kind of just goes to show one other thing is that you really only get good at doing these by doing these, okay? They're just not that easy to come into. Practice does make you better at these. We don't spend months and months on proofs, thank goodness. But it does in the process never get you to a point of feeling very, very comfortable with them. Just do the best you can to follow them through, and like I said, just learn from them. Okay, so I'm actually going to put up another one here. Okay, I'm going to do the second proof on the page, and this one again has to do with a parallelogram type proof. Actually, it doesn't tell us it's a parallelogram. We're trying to prove that, but I'm going to go ahead and draw another parallelogram because obviously that's what we're hoping to prove, right? So if I take a look at what's being given here, okay, they've said that I've got a quadrilateral. I've got a little bit of a, sorry about that. These drawing tools are very sensitive. Okay, let's see if I can't get that. That's close enough. All right, and all they've told me about it is I have one set of parallel sides and they happen to be congruent. Okay, that's pretty much all we're given on this one. And what we're trying to do is prove it's a parallelogram, which means what we're trying to prove is that DC and AB are parallel to each other. And usually when I'm given parallel lines, I'm going to go more in the direction of looking to see if I can find an easy triangle congruence for this one, rather than going through something like the supplements of angles that I did with the last proof. And it's usually a pretty good bet that something like this is going to work. So I'm going to take a look at this. Like, what if I were to draw this diagonal? Let's see if that's going to give me something that I can plan for. Okay, so I know I've got this is congruent to this, so I've got a side. And remember that if I have something like this, this is going to be another side, right? I could say that that's going to become another side. And can I get an angle in there? Okay, could I say that this angle is congruent to this angle? Well, I absolutely could, because I have this parallelism. Angle 1, actually I could just call this angle, no, I can't call it angle A because I've cut it. So I'm going to say angle 1 and angle 2 here. Angle 1 is congruent to angle 2 by alternate interior angles. If I know that both triangles are congruent to each other, then by CPCTC, I'm going to get DC is congruent to AB, and either by the fact that both pairs of opposite sides are congruent to each other, that the opposite sides will get me to a parallelogram. We do have, there's a proof on here. I'm just kind of scrolling through here, kind of looking to see, is there anything on here in my little toolkit that I can use? I don't really have anything that's easy to pick up as supplements, right? And kind of what I was looking down here is this opposite sides theorem and opposite angles theorem. And as it turns out, these are the theorems we're trying to prove. So if you look at the problem on your page, so I can't use a theorem that I'm trying to prove in order to prove it. So I'm going to have to go back a little bit, and that's actually, we haven't proven this one yet either. The parallelogram diagonal lemma, a diagonal of a parallelogram divides the parallelogram into two congruent triangles, which we've actually just now proven ourselves. talked our way through. I think I'm just going to go back to my whiteboard, and knowing that I can't rely on that opposite sides yet, I will from this point forward, I'm just going to go back to a more traditional way of approaching this proof, okay? It does take a few more steps if we can't use some of those shortcuts. But it's not too bad. This one is actually would be something that would be very familiar to you guys based on what you've done before. So I'm going to start with my givens, right? AD is congruent to BC, and AD is parallel to BC. So those are the two things that were given to me, right? Okay. And then I don't actually have to write a step that I created a diagonal through AC. It's on my diagram, okay? If you want to be super, super formal and technical about it, you could say, you know, AC is the diagonal of AB, CD, okay? That's kind of a, I don't know, that's a line segment. I don't even know how you would, it's by definition, right? Okay, but it's a line segment. I can connect any 2 points in space, right? Create a line, all right? So with 3, I could then say, okay, angle 1 is congruent to angle 2 by alternate interior angles. I already kind of thought this through, so this part's going to go pretty fast, right? AC is congruent to CA. That would be the same segment or reflexive property. Okay, and now I can make these 2 triangle congruency statements. Triangle, let's see, ACB is congruent to triangle, let's see here, make sure I get my orders. Let's see, if I do ACB, I would have to do CAD, right? I have to make sure I get my corresponding part order, cap. Okay, and that's by side, angle, side, right? I had this is one side, that's my angle, and this is my other side, okay? They both have these, that's side, angle, side, okay? And now I can make the statement, right, that, let's see, we're going to go to number 6. What am I trying to get to now? I want to prove that these two are parallel to each other, okay? And so from there, I guess I can use angles, right? Let's just call this angle 3 and angle 4, all right? So now I could say that angle 3 is congruent to angle 4, okay? Okay. And if alternate interior angles are congruent, well, the lines are parallel, right? So we could say AB is parallel to DC, right, by the converse of alternate interior angles, okay? Therefore, ABCD is a parallelogram, okay, by definition, if opposite sides are parallel, right? Okay. And if we were trying to prove that the opposite sides of a parallelogram were congruent to each other, well, we've got that covered by CPCTC as well, okay? So all of those properties of a parallelogram have been proven by these 2 theorems, okay? All right. I think that would hopefully give you guys some guidance. There are hints on the rest of these proofs. And if you would like a little bit of additional guidance, I'm happy to give it to you. I think what may have thrown some of you on this was the very first proof may have been, at least it was one of the hardest ones in here, and oftentimes the first one is easier. But like I said, just sometimes just hearing them kind of walked through, talked through what the thought process is, even if you came up with a different proof, it's helpful to see another approach. It might be more efficient, maybe it's less efficient. Feel free to share something with me that you think might have worked better, and I'll see you in class.